Welcome back to the next episode of the AI Ascent Podcast. In this episode, we're going to be talking with Ahmed Mustafa. He is the author of a new research paper titled Urdu Digital Text Word Optical Character Recognition Using Permuted Autoregressive Sequence Modeling. Welcome to the podcast, Ahmed.
Thank you for having me. It's my pleasure to be here.
Great. So we can jump into the questions here. So what degree do you have, and was this paper related to your university studies?
All right, so this paper is about optical character recognition. For those who do not know, optical character recognition, usually known as OCR, it is the technology or the tool that we use to be able to read text from images, right? So it's optical character recognition, you see? So if you have an image and that image has any text written on it, then you will use something like OCR. So it would be able to detect and recognize the text that is written on the image. So it could be an image of a digital document. It could be an image of, let's say, a banner out on the street, and you will take a picture of it, and then the computer will basically be able to recognize whatever text is written on the image. And my paper is on my master's thesis, so my postgraduate thesis. I did my postgraduate in robotics and artificial intelligence, and my master's thesis basically was creating an OCR system for my native language, which is the Urdu language. So that is what my paper is about, the approach that we used and what we learned and everything about that. So yeah.
Great. And so what are some of the challenges related to OCR for the Urdu language compared with other languages such as English or even languages such as Chinese?
So it is quite more complicated to deal with Urdu than it is with languages like English. And the primary reason for that is the change of the writing script that we use in Urdu. Okay, so in English, what we usually use is the Latin script, that comes from earlier Greek and earlier Latin, where you have individual characters, and each character has a unique sound, right? So the character for A has the sound of A, and the character for B has the sound for B, something like that. And there are two things that make English a easier language, I would say, for an OCR problem. And the reasons are, number one, the characters actually do not take a lot of different shapes, right? So for example, there are technically just two ways in which you can write any letter in the English alphabet. The capital version and the lowercase version, right? So the upper version and the lowercase version. These are only two ways in which you can write any character. So if we were to, for the sake of an example, if we just include, if we don't include any numbers, so no 0 to 9, no numerals, just talk corely about the alphabets, then English has 26 uppercase alphabets and 26 lowercase alphabets, right? So 26 letters in the uppercase and 26 letters in the lowercase in its alphabet. So that would become, I think, 52 total possibilities, and so that's it. With Urdu, that is not the case. In Urdu, each character can take up to 4 different shapes, dependent on where exactly that character appears in a single word. So for example, if we talk about, let's say, any character in the Urdu language, let's say there's this character called kaf. It's read kaf, but it's the pronunciation is the same as the pronunciation of the English letter K, right? So it's ka sound. the same sound that the letter K produces. So if there are four distinct, basically, ways that you can write kaf. If it is an isolated character, it is written in a different way. If it appears at the start of the word, it is in a separate way. If it's in the middle, it's a different way. If it's at the end, then it's also a different way. So the four possibilities of most Urdu character, I should say, not all, but most Urdu characters, there are four ways. It's the isolated way that it's written. If it comes in the beginning, if it comes in the middle, or if it comes in the end. So there are four total ways in which every individual English Urdu character can be written, at most. And there are around, I think, 36 characters in the Urdu alphabet. So all of a sudden, the number of possibilities just skyrocket as compared to English. So that makes it a more challenging problem. The second thing which makes it more challenging is how Urdu is written. Now, the best way to sort of make you understand this is, the difference between normal English and cursive English? What's the difference between the two? What do you think?
So in English, the difference is the characters all tied together. So cursive is made so that you don't have to raise your pen off the paper, and so all the letters are touching together, and so some of the letters look differently as a result of that.
Yeah, that's exactly what it is. And so if I were to ask you if you could make a guess, let's say, what do you think what would be easier, to read characters in a cursive script or read characters in the normal, simple English?
Well, I think in English it's a lot easier just to read the regular printed characters over the cursive characters. Since the regular printed characters are the more typical characters that we might see every single day, and the cursive characters are used less frequently.
Yeah, exactly. Even humans, I know I do, I find it a little harder to read cursive English because the characters are all connected. And if we as humans can find something more difficult, if the characters are connected together, then you can bet that an AI system, really a computer machine, would find it equally hard, if not harder. And so the problem with Urdu is, or a technical challenge with script like Urdu, is that the characters are not what we call isolated. So they're not isolated. For example, in simple English that you write, if you write the character A, B, C, or if you were to write your name, Luke, so you have L, then you have some space, very tiny space, but there's always some space, and then U, and then some tiny space, and then K, and then some tiny space, and then E. So there's always a little space between each character. And so that makes it easy to detect individual characters and then recognize what each character is. In Urdu, that's not the case. In Urdu, you have characters that are mostly connected to each other. And in case you're wondering, the Urdu script is pretty much exactly what the Persian or what the Arabic script is, right? With like some changes here and there, local regional changes for each language. So if you can't imagine Urdu in your head, just imagine Arabic script, right? So it's very connected and all the characters connect to each other. There are individual spaces between words, but within a word, within characters, there's rarely any space. So they're all connected. And then they're overhanging, one part of the character extends and shadows some previous character or some forthcoming character. So these are the kind of technical challenges that make the Urdu language very much difficult. With Chinese, as you said, Chinese. Now, Chinese also, I believe personally, might be an easier challenge, primarily because even in Chinese, you do not have you do not have connected characters. In fact, with Chinese, the thing with Chinese is not a phonetic script. So do you understand what that means, that Chinese is not a phonetic script?
Yeah, they use pictograms. They use
Exactly,
pictures.
exactly. They use pictograms. So for the Japanese fans out there, it's called kanji. It's the word the kanji is more famous to be used in Japanese because anime, because but kanji originally comes from Chinese, and so they do not have a single character representation for each individual sound, the way that phonetic scripts like Urdu and English and Arabic work. They have individual pictograms, individual letters, or individual representations of each of their different words in the Chinese language, and that makes it a very difficult language to learn because for every individual word in their vocabulary, they have a different representation for it. But for an OCR system, that actually makes the job a lot easier because you there are only as many number of possible outcomes as there are the number of words, so it's pretty finite actually. And the pictograms themselves in kanji are never connected, so they're isolated. They don't like connect with each other with lines and stuff. So I personally believe, it's my opinion, I haven't worked on the problem personally, but in my opinion, it would be easier to handle Chinese than it would be to handle something like Urdu. But that's just what I think. But definitely Urdu has its challenges when it comes to developing an OCR system for it.
I
So yeah.
see. Yeah, it sounds like a pretty complex task. So
Oh yeah.
what brought you? Yeah. So what brought you to working on this project of OCR for Urdu?
Well, number one, it was a master's thesis, right? This was what my supervisor, the professor that I was interested to work with, was interested in this problem. The reason for that was that he actually was a sort of a business-oriented person, and he wanted to develop a product out of it because it is the national language of my country, Pakistan. Uh, and Pakistan is still learning to adapt technology into its daily use, into daily use for the industry. And so this was the perfect moment. He thought that we should actually try to introduce a product that is made in Pakistan, belongs to Pakistan, and that is able to read Urdu text from digital documents. He had actually reached out to a lot of local industries like banks and factories and government offices that needed to process digital documents on a daily basis. And so what they would do is they would have like a lot of staff who would print documents, who would read them, and while they would be reading them, they would fill in the information, for on different computers. And so if you had an OCR system, all you need to do is you need to take a picture of the page, and then the information can be extracted automatically. So it's a very fast process. That is how we use technology and AI into to ease your life, really. And so that is what he wanted to do. That was his vision. And so when I asked him if he had any research problem for me for my thesis, for my master's, he said that this is the perfect problem, and I agreed. And so this is how the journey into Urdu OCR started for me.
I see. And
Yeah.
where did you get your data from?
Okay. The data came from a lot of places. So one thing we did very early on is that we discarded any handwritten text. So we decided that we will only deal with printed text. So text that is, in a certified Urdu font. So printed in a printed document. So no handwritten stuff. We were already facing a lot of challenges with digital Urdu, so digitally printed Urdu. So handwritten is just another beast. So we decided to just ignore that. And that meant that the data that we needed to get from had to come from either the printed literature, the printed documents, and let's say scene images, what we call scene images, right? So so if you go outside and you take pictures of any banner, any advertisement, anything that has Urdu or written on it. So we looked for data sets online. We hired annotators who would spend their entire like 4-hour, 5-hour shifts for months annotating data. We got a lot of Urdu literature books. We got them annotating on that, and so and we went outside. We did some live captures as well, and then we took screenshots from them so we could get data from there. So at the end of the day, we had quite a substantial amount of data. If I am not wrong, I think we had almost maybe close to 150,000 or 200,000 individual word images. I could be wrong there, honestly, but yeah, it was a big number nonetheless.
That's a pretty good size.
Yeah.
So how exactly were you able to label that data, and why did you move from the character level to the word level labeling?
Oh yeah, so we did do that. We started from character level labeling, and that meant that we would identify each individual character in a word, and then we will stitch them up, and that would be your result. That is the most human way to approach this. This is what we do as humans, right? So we essentially just so what we do is we, as humans, we take a look at an individual word and we, in our mind, break it down into individual characters, and then we identify each character, and then in our mind again we just chain them up, and that is how we read words. That was the most intuitive approach, and that is exactly the one that we decided to go with initially. But turns out that given the fact that Urdu has this connected script, isolating different characters became a huge challenge. Uh, Not just in terms of technological recognition, because that was hard, also because labeling the data was a pain. Imagine that you have like 50 words your on your screen that you have to individually label to create your data on which you have to train your model. So training on 50 words uh, or annotating 50 words takes, I guess, around maybe, I don't know, 2-3 minutes. But now imagine you have to annotate every single individual character in that, in every word, and all of a sudden now you're spending like 15 to 20 minutes on a single page. So you went from 2 to 3 minutes on a single page to 15 minutes on a single page, and so your process, is slowed down a lot, actually. So annotating the data this way became very taxing really fast. So we just decided to skip that, and we decided to move to word level recognition, which honestly is technologically more challenging for a neural network to learn, because now you have as many possible inputs as there are Urdu words in the vocabulary, right? So I'll try to explain it this way. If you choose character level labeling, so the question you're asking your computer is, what is this character? And there are only 36 possible characters and 4 possible shapes for each character. So it's a big number. It's more than 100 possibilities, but it is still 100 possibilities, which is within the range of what you can deal with. Now imagine changing that question and asking the computer, what is this word? And the machine has no idea of what the individual characters are. I'm trying to make it more of into an intuitive question so that you can understand that it is a much more technically challenging problem to ask a machine really what's this word based on the shape of the word, and that's it. We are not individually recognizing each and every character and then stitching them up. We're just throwing a word and we're saying, okay, what word could this be? And then they are trying to identify the characters and figuring it out from just the shape of the word. And so I think, but gladly, we are in the age of transformers, and they are very good. So visual transformers in general, I mean, they're amazing at what they do, and this approach worked eventually. And I'm really glad that we did not waste a lot of our time on character level data set annotation, because that would have taken us so much longer to get the same number of examples as we did this way.
Cool. Yeah, that makes sense. And so
Yeah.
what techniques did you use to pre-process your data before feeding it into the OCR system?
Just the standard ones that you use, the kind of techniques which you should use, I would say, before any image level data set is used to train the models. So if I'm trying to remember correctly, obviously there's stuff like you enhance the image, you correct the contrast, stuff like that. You discard any blurred images that you have that might add up, might add up as noise or something in your data set. So just sort of, that stuff. I think that was mostly what we did. There was also some images. There were also some images which have some skew in them. I remember. I think I mentioned it in the paper as well. So also one very important thing that you use whenever you deal with image level data set is you do data augmentation. So what that is, or what that means is, let's take the English language as an example. What is the most used character in the English language, or the most common character in the English language that you use on a daily basis?
Hmm. The most common letter, maybe is E.
I think it's A. I think A is used the most. Obviously, vowels are used a lot, so vowels are very common. Uh, I think the letter S appears the most times. The letter S appears in the most words, or most words start with the letter S, I think. That's also something. But then also there are characters which are rarely used. For example, X. If you open up a dictionary and check for the entries for X, X is very visibly used a lot less. And so when you're collecting data, you will find a lot of examples with A and E and S, and I, these sort of characters, and you will find very few examples of X appearing. And so this is called skew, data skew, which means that you have some classes which appear a lot more frequently than other classes. And so you have some classes which rarely appear. And so what can happen is, in this sort of cases, why this can be problematic is that if you're training a neural network, there is a chance that the neural network may start treating these examples with very few, sorry, these characters with very few examples as noise. So it will just start discarding them, because it will look at the frequency at which these characters are appearing, which will be quite small. And there's a chance, it may just deduce that this must be noise. I mean, this has the character X, that's noise. It doesn't appear as much for me to give it any significance. And that is a very common problem. So what we do is that we do data augmentation. This is called oversampling, and oversampling data augmentation techniques, so that we can produce more examples for the same character that we have in low frequency. Because we were dealing with in Urdu, for digitally printed text, that meant that I just wrote some code, some little program, and we procedurally generated characters that had a low frequency. So you can just, the way that you type on MS Word or type in any other text application, you can just type anything and the text will appear. This we did the same thing, but automated. So we did it in runtime, that these images will be generated, and that is what we did. Also introducing color shifts and everything. So just basic image data augmentation techniques were used for this uh, before we moved on to the training part.
I see.
Yeah. Yeah.
So How did you address the challenge of managing Urdu's character positional variations? So the initial, medial, final, and isolated in your model. And what impact did treating each positional variant as a separate label have on the model's
Mhm.
complexity and performance?
So I'll answer the second part first because it's easier. It made it harder, obviously. It made the problem much harder because there's a lot of I think a big lesson that we learned from this entire journey is to not underestimate modern neural network architectures. So we started from a very computer vision based approach because we are students of the old generation that initially started to implement OCR and other applications, image processing applications using basic computer vision techniques. And what the way that we approach this problem is exactly the way I think anyone would, which is breaking it down into individual steps and then trying to solve each individual mini problem one at a time. But we realized after some time that maybe we did not need to do that. And I'll give you an example. So imagine overlapping characters, right? Imagine characters that are, you can confuse them for another character just because they're appearing in the same frame, even though they are different characters. And so we were like, okay, what about if we figure out some way to distinguish them? And so we write a totally separate algorithm just to be able to distinguish between the two. And then we train on that, try to run inference on that example. Uh, but turns out that the best way of dealing with it was to just trust the architecture, which means don't do anything. Don't do anything. Just get enough data, and get a strong enough architecture for the neural network. And turns out it will just learn by itself. So, that was something that I think a learning experience that we did need to go through because it made the job a little easier because it's basically like throwing a lot of data to a neural network and letting it figure out all the complexities. Now, obviously, the more complex the problem is, the more data you need, the more stronger of an architecture you need, and the more sensitive the entire training process becomes. But that's part of research. That's what you sort of learn to do over time. And this is, I think, so that's the answer to the second question. What was the first part of the question? How did we address the individual characters, individual shapes?
Yeah, how did you address the challenge of managing the positional variations in the characters?
So what we did was this was the only, I think, the only extra thing that we did. We decided to treat each individual shape that a character can take as its own output class. So if there was, I gave you the example of the letter calf, right? So if calf is written, and there are four ways to write it, instead of mapping all four to one output, we map these four to four different outputs, and so it was one-to-one mapping. You know, we could have gone 4-to-1 as well, but it just seemed to make more sense in our head. I don't think it would have made much of a difference either way, but that is what we decided to do. So yeah.
Okay. And so what is the permuted autoregressive sequence architecture? And why did you think it might be useful in this context?
Hmm. Uh, so the question that you asked in the quite recently right now about dealing with positions and dealing with overlaps. So essentially, as I said, we decided to not focus on the problems individually, but let the architecture, the neural network handle it. And so we are making the neural network do all the heavy lifting for us. And that meant that the neural network needs to be in itself pretty uh, technically advanced. It needs to be able to capture all these, nuances in the Urdu script. And this was our entire research statement, honestly. How can we make a neural network strong enough that it can uh, recognize each individual character, each individual shapes, overlapping, hanging characters, whatever, characters with diacritics, and all that. So there were a lot of techniques that we tried, a lot of literature that we read, uh, the way that people in the past had approached Urdu OCR, or people in the past had approached similar scripts like Persian and Arabic. We looked into that and we applied their techniques. Every time there was some sort of improvement. But then we discovered this paper, which is, I think, it's a permuted autoregressive. It's on permuted autoregressive sequencing. It's a very heavy loaded word, permuted autoregressive sequencing. So it's a very technically challenging word. But what it essentially means is that you take a sequence of characters, a sequence of anything really, but for our case, a sequence of characters, and then you perform permutations on those characters. And permutations mean you shuffle them up. You shuffle them up and you create a new sequence. Then you shuffle it up, create a new sequence. Shuffle it up, and you do that a number of times. And then you try to calculate the relationship between each character combination in that permutation. For example, if we take your name again, Luke, Luke, one possible permutation or shuffling for it could be UKEL, right? And then we calculate what is the individual relationship between U and L and U and E and U and K based on their position in the shuffled or permuted word. So this was the inspiration behind permuted autoregressive sequencing. Uh, the problem that I think the original paper on permuted autoregressive sequencing, it was about something else. It was they used it for the English language, and they were trying to deal with something else. But when we read it, when me and my team, we read about this approach, you get this sort of a hunch, right? That maybe this is what we need to cater for the connected characters and everything uh, in the Urdu script. And this was just a hunch. This was nothing more than that. And this was not a new thing. As researchers, you often get these hunches that, okay, you know what, this might work. And most often it doesn't work. It doesn't work out a lot of the times, but sometimes it does. Eventually it does. This was one of those techniques which actually ended up helping a lot. I mean, we saw a very good increase in our accuracy, and once it started working, then we were like, oh yeah, of course it worked. I mean, it makes total sense now. But initially it wasn't making it was just a guess. Then, hypothetically speaking, it makes a lot of sense, it should work, let's try. But this was the sort of statement that we have said for a lot of things as well, and they did not turn out too well. So we were very skeptical about this one as well. But if this one worked, and as I said, in retrospect, it makes total sense that it did. But we decided to apply it to a small data set. It worked well. We tried to scale it up. It scaled up pretty well as well. Maybe not as it's very computationally challenging though, because you're calculating permutations for each individual example. So you're basically multiplying your data set by scaling it up by a certain amount. So it takes longer to train. It's more computationally expensive, but it did bring us the results that we kind of were looking for. So that's a plus. So yeah, that is how the permuted autoregressive sequencing, or PARSeq as it's called, approach, came into being used.
Very interesting.
Yeah.
So the next question is, what is the character error rate, and why did you choose it as your primary metric for evaluating your Urdu OCR system?
So character error rate is the primary metric that most people use for OCR systems. And all it does is it gives you a score from 0 to 100, let's say, of how correct is your uh, recognition, right? So imagine that you have 3 characters and your system is able to, detect 1 letter incorrectly and 2 letters correctly. Recognize there's 1 letter is incorrect and 2 letters are correct. So you would say that the accuracy is 66%, right? 66.6%, because 2 characters are correct out of 3. But it's actually a little bit more complicated than that. Not too complicated, just a bit complicated. Because what if, what if, we'll go with the same example, your name. So what if instead of recognizing Luke as Luke, Luke, it recognized it as Lukei. So it added an I at the end. So now what is the accuracy? It is a little bit more interesting question. Some would say that it's 80%. Some would say, that it's 100 because it did recognize everything correctly. It just added something at the end. But if you are adding something at the end, that means it's incorrect. It's not completely correct. It shouldn't be able to make any deletions. It should not be able to make any additions. It should not be able to make any substitutions. So instead of Luke, it was Luka. That is also incorrect. And so character error rate, it is a very simple formula. It's not too complicated. It takes in the number of substitutions, the number of additions, and the number of deletions that there are in the predicted text that were not in the original text. And so it uses those to calculate the final accuracy. And that's just it. It's very simple.
Perfect. And what were the final results of the OCR, or of the CER on the test set?
I think it was around. The funny thing is the character error rate is not accuracy, it's the opposite of accuracy. So it's calculating how much error there is, right? So if you have a CER of 100%, that means you butchered it. Like that, there is no worse way of doing it. so 0% error rate is 100% accuracy, and 0% accuracy is 100% error rate. So it's the opposite of accuracy. So the low the CER, the better the result. And on our test data set, we got an character error rate. If I'm not wrong, it was somewhere around 13% or 12%. I think, you know what? Actually, let me verify. I think it was around 17%. Oh yeah, so 17%. Exactly. So 17%. We had the final. So it means that there's a 17% chance that there would be any error in the final prediction, and a 83% chance that the character is actually pretty perfect. And I think that's a pretty good accuracy given the challenge of the problem. And it was actually more than what Google Vision was able to give us. Google Vision was bad. It was like 35 or something. If I'm not incorrect. I guess that is also written somewhere in my.
Yeah, it was also written in your paper that Google Vision recorded a CER of 89.1%.
Oh yeah, it was 89.1%. Yeah, exactly. I'm remembering it now. So the reason was Google Vision performed really good on images which were very simple. You take a white background, you write a digital text on it, perfect. As soon as you go into a little bit more complicated examples, if you're looking at the paper, you can see the kind of examples that we use in figure one. It's on the last page. So in figure one, we are talking about the kind of examples that we had, uh, that we were not able to perform very well on, right? And but you can just take a look at these and you can imagine the kind of images that we had, right? And so on these types of images, Google Vision it doesn't work too well. I don't know. Maybe it's better now. This is 2 years ago, two years ago almost, but this it wasn't really working too well. We were able to perform a much better job. Although I will say, as an engineer myself, I do recognize that our test set had the same data distribution as the training set. So it makes a lot of sense that given our training accuracy was high and there was no overfitting, that it would perform this good on the test set. Now, this is just me saying something as an engineer, because I do realize that data distributions do matter. And maybe the data distribution that the Google Vision data is trained on is not very much overlapping with our distribution. But again, it's Google Vision, so you would imagine that maybe it still would be. So getting a higher or lower CER and a higher accuracy than that was pretty good. It was pretty neat.
Interesting. Yeah, that is very good.
Mhm.
So can you discuss some of the factors that could reduce the accuracy of your model, such as non-horizontal orientation, blur, or background interference?
Yeah, that's exactly what it was. Those are exactly the things that ended up sort of messing with the accuracy and messing with the results. If there was too much blur, the image was too blurred, it wouldn't perform very well, which makes sense. If we had slight rotations or too much rotations, it usually performed bad. Not always, but usually performed bad, which basically goes to show that we did not have a lot of blurred and a lot of rotated images in our data set, which I guess we should have. Then there were any sort of images which had any patterns either overlaying or beneath the word, that would cause it to have bad predictions. Also, punctuation marks, any sort of punctuation mark would, I noticed, had a very decent chance of messing up with the prediction. And all of these really just point towards the same problem if you were trying to solve it, and that problem is lack of diversity in the dataset. If we had more blurred images, more images with unique orientations, images with overlaps and patterns and punctuations, maybe we could have had a higher accuracy. But that's just uh, you can always try again.
Yep. So looking back on this project, what were the most surprising or rewarding aspects of working on OCR for Urdu?
The application of it. The first time we built something out of it and we showed it to it was a local bank in Pakistan. We showed it to them. We showed them that it is working. They actually brought a document with them, and they wanted to test it in real time, which was, I think, a pretty smart move on their end and made us very nervous. But it worked pretty well, actually. It worked pretty fine because it was just a digitally printed document. And we were we got pretty good at just detecting black text on white background. That became like the easiest thing over time. And that is what they brought. They just brought black text on white background and they took a picture of it with their phone. They sent us the picture. We ran the inference on it, and they were pretty surprised by the results. And whatever minor errors there were, we told them that this will be a proper MLOps type thing where we will deploy our system and then we will keep collecting their data with their permission, obviously. And then we will keep training our model on their data so that over time, in the next 3 to 6 months, the accuracy will shoot up because we are constantly training it on the type of data that they use in their daily operations. And they were satisfied. We built the project, we deployed it. It's working in multiple uh, places right now as we speak, and that is the most rewarding part of it. Actually, I actually went to one of these banks recently, and they like scanned a document, and the results showed up. And I was just thinking that, oh my God, I built this. It was pretty cool to think about that way.
That's awesome.
Yeah, it is.
So what's next for your career?
What's next for my career? That's a challenging question. So right now I am working in the industry for around 5 years. Uh, I'm working in a lot of different sectors. I'm working with the obviously working on problems like these. I'm also working in the healthcare industry. We recently published a paper on predicting cancer. Did we the chances of cancer reoccurring in a liver transplant patient, right? So usually what happens is that if someone has liver cancer, you can always get a transplant and that solves the issue, but that's not always the case. Sometimes the cancer can come back, you know and if the cancer comes back, uh, first of all, it's very sad, obviously. Secondly, you just wasted a healthy liver, because you took a healthy liver from a healthy person. You don't always take the full liver, but still, you took a healthy liver, you transplanted it into someone, and then that patient, the cancer relapsed, and so you wasted a healthy liver on a patient. And so there are standard medical techniques that you can use to pre-identify the chances that a certain patient will have this recurrence of cancer after some time or not. So let's say that there's a patient who has liver cancer, and he comes to me and he says, I need a liver transplant. I will do the tests and I will come up with a number between 0 to 100, let's say. Uh, and that number will tell me what are the chances that even after the transplant, the cancer will just recur. And if the number is like 90%, so there's a 90% chance that uh, the cancer will come back, I won't be going forward with the transplant, because why would you? If there's a 90% chance that the cancer will just come back. But if there is like a 10% chance, then you might go ahead with it. You will be like, you know what, that's decent. 10% is good. So there are existing criteria that exist that are already in use. What we did was we sort of we built a machine learning model out of it. We collaborated with the international hospital, Shifa Hospital. I think it's pretty famous, at least in the Middle East. The Shifa Hospital. We worked with it. We got some data from them, a lot of data actually from them in medical terms, and then we trained a model on it. And the system that they were using had 65% accuracy. We had around 78% accuracy. It was a huge deal for them as well. We deployed the system there. They're using it today. It's pretty cool. So we got a publication out of it. My current job is also in healthcare. We give healthcare solutions powered by AI. I'm also working in the education sector. So there's a lot that I'm doing right now in terms of AI application in the industry. But I'm also looking forward to one of my other passions, and that is robotics. I am very much passionate about robotics, robotic applications, and right now I'm thinking about uh, maybe going for a PhD at around this time in my career. I think it's a good time. Uh, I have I have a postgraduate degree. I have had significant experience in industry and also some research experience as well here and there in multiple industries. I think I guess either I would go for a PhD or I would continue working towards practical applications that use AI in, you know, daily use. Because Pakistan is one of those countries which is still on its way to use modern technology in its daily use, and I love to be a part of it. So it's one of those two things. Hopefully, inshallah. Yeah.
That's great. And my last question is, what advice do you have for future researchers in the area of OCR for languages such as Urdu?
Literature review, literature review, literature review. Read a lot of literature. There's a very good chance that the way that you are trying to approach the problem has already been addressed in a certain way. Do not underestimate the importance of data. And one thing that I would like to say to pretty much everyone is that we have come at a stage in AI and machine learning that we now have neural architectures like transformers, such that if you throw just enough data at them, they're able to learn the entire language and its knowledge corpus. I mean, I'm talking about ChatGPT and Gemini, you know, and all these LLMs, Llama and Claude, all of these LLMs that are available. We just threw a lot of data at them, and over time, they not only picked up on the languages, but the common facts and figures and systems, all of these things. So we have come at a stage where just by throwing enough data at a machine learning model, it just starts working eventually. So if you're trying to approach a complicated problem, first of all, remind yourself that there is a machine learning model that speaks your language better than you, which means whatever problem that you're trying to solve can most likely be solved by machine learning. That's the first thing. So I believe there is no problem hard enough that maybe you will say, you know what, machine learning can't solve it. It will solve it. I am very certain it will. Now you have AI video generations. You can write a text and it will generate a video out of it. So machine learning can handle pretty much any problem you throw at it. At this point, all you need, your limitation is data. So focus on as much data as you can. Data is the key. It's the currency. It is what ties directly to your accuracy. Get as much data as you can and do as much literature review as you can. And just by making sure that you do these two things, you will have a very good chance of succeeding at whatever your ML related research problem is.
Awesome. Perfect. Thanks for coming on the podcast, Ahmad.
It was my pleasure. Thank you so much for having me. It is so interesting to talk about these things. And if you ever want to, know anything more, you can always, ask me. There's no worries about it.
Perfect. Also, is there anything that you want to shout out? Your LinkedIn, any website or company?
So yeah, I do have a website. I actually built it just a while ago. It still is filled with some dummy data because I'm still working on it. But hopefully by the time this comes out, maybe it will be functional. So I'll provide a link to you. You can just, add it in the description. My LinkedIn, sure, people can also go visit that. I'll provide it there as well. Anyone who's listening to it, who's kind of interested in this sort of these conversations and just want to reach out for anything else, I am always available. Just drop me an email, and I will make sure that I try my best to get back at you. And it's really good that people in today's day and age can collaborate and work together on problems from all across the world, bringing their knowledge and their perspectives. And I love to collaborate with people like that. So if anyone has any questions or any ideas that they want to discuss or share, I would love to hear them. So yeah, feel free to reach me out.
Perfect. Sounds good. All right. I really appreciate the time, and I'm looking forward to staying in touch.
Yeah, me too. This was amazing, and I'm really glad that you reached out. I'm really glad that we did this. And yeah, it's my pleasure.